So far we have talked about covalent bonding because they've been sharing electrons with the Lewis structures. It's all talking about sharing electrons. The other types of bonding are ionic bonding and metallic bonding. Oh, resonance structures you can cross out. We aren't going to... Let me skip them. Yeah. Yep. Yeah, I wanted both sheets. Resonance structures. Cross out resonance structures. So we've talked about what an ionic bond is. It's because we have a cation and an anion, and when the positive and negative are close to each other, they're bonded together. So when they have equal numbers of cations and anions in a bond or in a compound, that makes it neutral. So sodium chloride is an example. You can't really isolate it and examine it like a molecule, so you can't isolate just one sodium and chlorine bonded together because they make up this crystal lattice, it's called. That helps stabilizes it. And so what it kind of looks like is you have this sodium that's surrounded by chlorines, and all the chlorines are surrounded by sodium, and it's a 3D structure, so we make this large 3D shape. What does sodium chloride, like if you look at table salt, what shape do all those little salt crystals make? Have you ever looked at them real close? What? They make little cubes. So today at lunch, put some salt on your tray and look at them real close, and you should see every single one of those would be a little cube. It's because of their lattice structure. Sodium chloride looks like this. We'd have, here you'll see red. So we'd have sodium, and it's surrounded by chlorines. So we have all these chlorines surrounding it. But then each of these chlorines is surrounded by sodiums. And this one's surrounded by sodium. So you can just see how it becomes larger and larger. And then the sodiums are all surrounded by chlorines again. And we just get to be a larger and larger structure. And so you can see they look like little squares, but it's a 3D structure, so there's actually a chlorine coming out from this sodium towards us and one going back away from us. So we actually form a cube. So if you take a bigger chunk of salt, when you break it up, it will almost always break into cubes because of its lattice structure. And there's several different shapes, and your book lists a bunch of different shapes that they can form. We aren't going to worry about that so much. The lattice energy, though, is the energy that it takes to break any of those bonds, kind of like bond energy with covalent bonds. So for ionic versus molecular compounds, some different traits of both. Ionic bonds are stronger bonds than molecular bonds, so ionic bonds are stronger than covalent bonds. They usually have higher melting and boiling point. Because they're stronger bonds, it takes more energy to break the bonds, so they would have a higher melting and boiling point. They're usually hard but brittle. Think about salt. Salt is easily breakable. Brittle means you can break it pretty easily. They're electrical conductors when dissolved. If you have a salt water solution, that will conduct electricity, whereas if you just had pure H2O, there's no other ions in it, it would not conduct electricity. They may separate when they're dissolved, ionic. Usually the ions, cations and anions, will separate from each other. With the electrical conductor, if you did Mythbusters do? They did one where they put a hairdryer in a tub or toaster in a tub. Does anyone see that one? I can't remember if they tested pure water versus like tap water or not. But the pure water really shouldn't conduct electricity, so you wouldn't get electrocuted. But if you had tap water, it has a lot of ions in it, and that's what conducts electricity. And then metallic bonding is a chemical bond that results from attractions between metal atoms and a surrounding sea of electrons. Now the reason why they call it the sea of electrons, because the metal bonds are occurring in the transition metals, so in the D block. If the element is in the D block, its highest energy level, like let's look at iron. Iron's highest energy level is 4, but it still has electrons in the D sublevel, and those D sublevel electrons can kind of move into the P orbital. There's going to be lots of empty orbitals that the electrons can move through, and so that's why metals have their specific properties. It gives them the ability to be malleable and ductile and all those properties. And they're high electrical and thermal conductivity because electrons are able to move from different orbitals. They're able to absorb many light frequencies. They're shiny. What's another name for shiny? Luster. They're lustrous. They have high luster. Lustrous. And they're malleable. Remember, malleable would be they can be pounded into sheets, and you could bend these sheets of metal. Ductile is able to be pulled into thin wire. And then they have a high heat of vaporization because they have a lot stronger bond strength because of those electrons able to move throughout the different orbitals. And, yep, we are not going to go on to VSCPR theory. We're going to do the, oh, we did that. Oh, in the notes we had, it was, if you look on the page before, it has the same thing. Yep. So you really can cross it out because all that information's on the page before it.